welcome Professor Aldo Jorio to give us a talk. Professor Jorio got his bachelor's at UFMG in 1994, got his PhD there too in 1999. He spent a year at the Institut Laue-Langevin and did his postdoc in 2000-2001 at MIT. And since 2002, he's a professor at the Physics Institute at Federal University of Minas Gerais. And I have to apologize that when I sent the messages today, I translated, I said Federal University of Belo Horizonte in Minas Gerais, and it's the opposite. So sorry about that. So today, Professor Jorio is going to talk to us about localized phonons and electrons in two-dimensional systems. So thank you very much for accepting our invitation, and the microphone is yours.
Well, thank you, George, for the invitation. It's nice to be here with you. So let me start very slowly here with some concepts that actually comes from economics. These are called economic cycles that was identified by this Russian economist called Kondratiev. And it's very interesting for us scientists, let's say like this, that to see that the heights and depressions of capitalism, they are somehow connected to technological innovations. You start with the first industrial revolution, and then the age of steams and railways, age of steel and heavy engineering, and then comes in the 90s the electricity. We start to control electrons, right? And then it comes the age of information telecommunication. We move from electricity to electronics. So we dominate more precisely the behavior of the electrons, and then we can build all this machinery that we are using here for this online discussion. And we are today in a sort of depression of the economics worldwide system, and we expect that the next cycle will be related to sustainability, to an even better control of our use of energy, and then green hydrogen and all the concepts come, because we cannot keep growing and using more and more energy as we are doing, right? And in this context, it's interesting to look into the two-dimensional systems. So this is one of the topics of my talk. When you think of hexagonal boron nitride, this is it's a large gap insulator. Okay, it's a 6 electron volts of gap between the conduction and valence band. If you take on the other side, if you take graphene is a semi-metal or a zero gap semiconductor. And in the middle, you have a sort of materials that like transition metal decalcogenides or black phosphorus, where you can somehow tune and control the gap. And this allows you, for example, if you think of optics, this allows you to do optoelectronic devices that can span a very long, large area of radio frequencies from ultraviolet down to radio waves. Okay. And so this was one aspect of this talk, the 2D system. And the other aspect is I'll be talking a lot about the technique that is the Raman spectroscopy. And the Raman spectroscopy is simply explained with this phonon diagram. If you have a photon that comes, the photon interacts with the material and it leaves a quantum of energy in the material. Usually is a phonon. The phonon is a quantum of atomic vibrations. And the scattered light will have the energy of the incident laser minus, actually it could be plus also, but we keep on the so-called Stokes scattering. The Stokes scattering is when the incoming light loses energy to the material, and the scattered light carries this information. And this is very informative for the material, because the material is a combination of the atoms and how they are bound to each other. If you think, for example, this would be the Raman spectrum of graphite, a very old one, okay, 1970. And the peak that you see here, they call it G peak. The G from graphite is the stretching of the carbon-carbon vibration. So this is stretching because of the mass of the atom and because of the strength of the bondings has a given energy. So it gives a very characteristic peak, and you can define very well that this is graphite, or even a single sheet of graphite that is the graphene. And if you go and you look very different carbon-based materials from, you can think of a carbon nanotube, which is a graphene rolled up into a tube, or into amorphous carbon. There will be signatures that are similar. For example, this frequency, as I said, is the carbon-carbon stretching, but you also have some differences. And what happens is that every time you change the material a little bit, either if you roll it up into a nanotube, or if you take the sheets of graphene apart from graphite, or if you make vacancies, defects, all these things will appear. And one interesting aspect here is, okay, here again, this peak that you see in the optical spectrum, the Raman spectrum, is the G peak. But you have one peak appearing here that only appears when you have defects on graphene. And if you increase the amount of defects, you increase the amount of, let's say, the contribution to this peak in the spectrum. And with this information, you can characterize the amorphization of a graphene sheet, okay? This has been very largely used in all the industry that utilizes carbon as a material, okay? And this is one this is one paper that we have in 2010, where we did an experiment that was like this. We took a sheet of graphene and we bombarded with ions. Okay, so when the ion hit the graphene, it generates a disturbance on a given area that I call it this red area here. So this red area is the area that has been damaged by the ion impact. And if you keep bombarding the graphene, you will increase the number of defects up to the point that you completely destroy the material, okay? And then you can make one interesting picture, that is, take those two Raman peaks. This is the defect peak, and this is the usual graphite peak or graphene peak. Take the ratio and increases the amount of defect, or decreases the LD. LD is the distance between defects, okay? The average distance among defects. And what you see is that as you decrease the distance among defects, the defect peak will increase, but then it reaches a maximum and it decreases. And what we realized is that this maximum is, you already saw that there is a green area here. I didn't talk about this green area. I explained the red, that is the damaged. And the green area is an interesting aspect where if an electron generating the Raman scattering happens to be in this range, in this area here, it knows there is a defect there. If you are far away, you don't know. So there is a correlation area here, which is inside this range, this area that's green. The process knows there is a defect there. The electronic structure is connected to that defect. If you are far away, it's not. So what happens is that you reach a maximum when there is a coalescence of this green region. And above this situation, what you do is you destroy the material. So this is why it decays, okay? Everything that I show you here is done at the macroscopic level. We illuminate the amount of material with all these things, and then you can do something that is more interesting. You can have defects that are points, or you can have defects that are grain boundaries. And the grain boundaries will again have the grain boundary itself and the region, which is green, where the electronic structure fills the defect region that's there, okay? And since we have two information now, one is the distance between point defects and the other is the size or the distance between crystallites, you can, using two spectroscopic information, you can disentangle the amount of point defect and line defect that you have. If you look, for example, at the width of a Raman peak, we know the width of a peak is related to the certainty that you have on this energy. And when you decrease the certainty or you decrease the size of the crystallite, the peak broadens, okay? And here is again this defect induced to G-band area. And with this two-dimensional plot, you can make a kind of phase diagram of amorphization that is, if your samples follow this line, it has only line defects. It follows these lines, only point defects. And in the middle, you have everything as we have here, okay? So all this story is on what we call, let me call it a micro-Raman. We are in the microscopic range, and we want to evolve and go into the nanoscopic range. We want to do nano optics or nano-Raman imaging, okay? What you see here are those grain boundaries, like I showed. This is a piece of graphene, okay, with the grain boundaries. And what you have, this image is made with STM, with scanning tunneling microscopy, because the electronic structure at the grain boundary is different from the electronic structure at the nice organized graphene. And then you can image the graphene with these defects. And what you see here, this is a work that we did back in 2017-18. You start to see optically the same thing that you see. You have to have good eyes, okay? You see that the structure that you see here, this is an optical image, is not the STM, not scanning probe. You also see the grain boundaries showing up there. You also see it here, the same here. So we are getting to, and notice this is 600 nanometers. So you are starting to see optically the grain boundaries. And if I go even further, here is the image of graphene. The graphene ends here. And this is an image of this defect-induced peak. And you can see that the defect range or the grain, the end of graphene, you can image with a resolution much on the order of nanometers, okay? It's like if you are here imaging exactly this green area because the graphene ended here, okay? And what I want to show you here is how we build device to do this kind of optical measurements and how we could then image the emission of light when you are imaging this defect-induced light or D-band next to an edge. Okay, so what is the optical limitation of light? If you have a wave that is propagating and it reaches we have an aperture here, okay? That you have this yellow thing stopping the light, but this is open. And if you let the light pass, it will go, when the aperture is large, it will go more or less like the geometric optics, where you can trace rays of light that goes straight, okay? But what happens if I close this aperture a lot to a point that the aperture it has a size that is about the same size of the light wavelength? Then you have diffraction, okay? This means that if you have two emitting objects that are separated by less than, well, this is the actual number, but roughly speaking, if you have an object that, two objects that are apart from each other by less than half of the wavelength, you cannot separate these two objects because of the diffraction, okay? If we go historically, this is known for a long time, okay? This is Ernest Abbe in Jena. Ernest Abbe was on the source of the beginning of the optical institutes, etc., in Jena. So he knew already, he developed these diffraction limit optics. And if you go a step further, we see that in 1928, Ernest Singe, he made a proposal, which was the following. What if I could go very close to the object and look very close, so I don't let the diffraction kill my imaging resolution, okay? So he proposed this in 1928, and in the year of 2000, researchers at ETH, in the group of Renato Zenobi, they demonstrated that if we use the cantilever, or if we use the system of scanning probe to get very close to a molecule, you can see this molecule very nicely. And then because you got very close, you can overcome the diffraction limit and reach our desired nano optics, okay? This is summarized on this plot that I call here, in this axis here, I'm putting the spatial resolution. So this is millimeter, micrometer, and nanometer. So if I take a scanning probe microscope, this scanning probe microscope like STM goes down to atomic resolution, okay? But here you have some sort of level of information, okay? Raman spectroscopy can give you a lot of information, but because it's optics, you cannot cross the diffraction limit. If we are able to do what Renato Zenobi and his group did, join Raman spectroscopy with scanning probe and look into the Raman emission very close to the object, I can populate this area here where I have high resolution and high molecular information with this technique, which is called tip-enhanced Raman spectroscopy, okay? But to understand the development of the technique, this is the year, okay? It starts here in 1920, and this is the number of published paper in logarithmic scale. And it starts here in 1930, when Raman, an Indian professor, discovered the Raman effect. And then, of course, it starts growing, and up to date, today you have like more than 10 to the 5 papers utilizing Raman spectroscopy being published by year, okay? And then you have another technique that was developed that is surface-enhanced Raman spectroscopy, where you use plasmonic structures to enhance the molecular information in a surface. And you had the development of the scanning probe technique. When you put these things together, you can create the near field optics, and then lately the tip-enhanced Raman spectroscopy. Okay, this is how these techniques showed up. Let's see how to implement. So to do optics or to do Raman spectroscopy, you shine a laser using a microscope into the sample, and then you get the scattered light and you analyze. Okay, so this is technically the same thing that this Feynman diagram is showing here. The laser comes, interact with the material, and the scattered light will be illuminated. To make the nano optics to work, I have to improve the optical setup, because I have to modulate the light polarization in such a way that the light will couple very nicely to a nano antenna. The nano antenna is the scanning probe system. So here is a zoom. the light will excite a nano antenna, and this nano antenna will be controlled by a scanning probe system. Can be AFM, STM, or any of these scanning probe techniques. And if you move the nano antenna, you make images, as I will show you here. So these are two Raman images. When I say Raman images, it means we are plotting the intensity of a given Raman peak. In this case, are Raman peaks from defects in graphene that I already explained to you a lot. So there is a sheet of graphene here. There is another sheet of graphene here. And with a focused ion beam, we came and we made a picture here. And we came and we made another picture here. And the focused ion beam can focalize and make pictures very nicely with a resolution that is much smaller than the wavelength of light. And if I do microscopy with a microscope, I cannot resolve. If I use the nanoscope, which is I land the nano antenna and I do the image now with the nano antenna, I can nicely see that what was drawn here was the world map. Here's South America, and Brazil is somewhere here. Here's Africa, Oceania, and etc. Okay, and the image down here is the logo of UFMG. Okay, my host, my home. And again, notice that this is 500 nanometers, and the resolution I have here is much lower than that. So we are imaging things below the diffraction limit. So the pictures you see here now, they are the picture of the system. Okay, this system that we worked to develop this system in the last 20 years, and we have a spin-off now. It's 4 of our previous students. They initiated a company to produce and sell this system that they helped developing inside our laboratory. So they developed all the electronics, all the optical parts, the scanning head that controls the nano antenna, and also the softwares to control the system and to analyze the spectrum. We had to develop softwares because when you do this nano imaging, the information that you have for every nano position is one spectrum. So the amount of information is so large that you have to be able to process this information in real time to take decisions, etc. So everything was developed. Okay. And also a very important point was the antenna itself. We had to develop an antenna that was highly efficient. And this is what you see here. This yellow part here is a cartoon of the antenna, which is made by gold. This red part that you see here is representing the light being focalized with a microscope objective into a sample of graphene. And then you come with the nano antenna, and the nano antenna will focalize the field in this very end. And this is what gives you this high resolution. And this nano antenna is a plasmonic structure, because when you have this micropyramid and this nanopyramid, what happens is that this nanopyramid here becomes a cavity for a plasmonic oscillation. And this cavity has a resonance. When you change the L, there is a specific size for this cavity here that will be in resonance with your given laser wavelength. Okay. And finally, how to produce such a thing, because this is very small. Okay, the apex of this pyramid here is in the order of 10 nanometers. And the way we produce this is actually using silicon technology. Imagine that this is a piece of silicon wafer, okay? And here you have a cover of silicon oxide. So you open a hole in the silicon oxide and you throw an acid. The acid will not make corrosion on the silicon oxide, will only make corrosion in the silicon itself. And then it opens a hole. And this hole will respect the silicon crystallographic orientations, and this will actually become like a pyramid. and then you oxide the silicon again, and you open a hole again, and then you do the process of corrosion again. And then you have the shape of our nano antenna. Here you evaporate gold, and then you come with a glue, and you detach the gold, okay? And the importance of this micro nanofabrication is that you generate this cavity, and you can generate this cavity in a very reproducible way. You can make many tips, and like those who work with scanning probe techniques, you know that you have to replace the tip if you break it. And the important result, which is shown here, is that, okay, the green spectrum that you see is the spectrum that you obtain in a large area of the spot when you have the laser focalized with a microscope objective. Then if you land the tip, the signal enhances very strongly, and then you have a signal much stronger here, but this signal, very strong signal, comes from a very small area, which is 10 nanometers inside, which is the apex of this antenna. And now if I scan the antenna all over, I can make images of the system, okay? And let's give examples of what we do with this. There is an interesting paper that was published in 2012 by some Korean fellows, where they show that if you look into the frequency of vibration of some Raman peaks in graphene, you can, interestingly, you can characterize strain and doping, okay? And if you use two frequencies, like we did for line defects and point defects, if you have two information, you can disentangle doping from strain. And then they do it nicely for a sheet of graphene. So what you have colorized here is a sheet of graphene, and the different colors are different strain and doping, okay? But this was done with a microscope, and every pixel you have on this image is actually 1 micron. And what we can do now is you take this 1 pixel and you do the scanning with a much higher resolution. So now you have, this is 1 micron, the entire piece is 1 micron. And we show that inside this one spectrum from the Korean fellows, you also have strain and doping localized in a much smaller scale, in a nanoscale, as compared to the large scale that was characterized by the Koreans. Okay, and let's do some interesting, let's say, device characterization and understanding with this. Let's say that you have silicon oxide is the gray, okay, and then you put a material here that's represented in green. This material is talc. And then we know talc strongly dope the material if you put it on top of the talc. Okay, so let's lay down a sheet of graphene, and half will be on the talc and the other half will be on the silicon oxide. And later you could look at MOS2 also, but let's stick on the graphene here. If I make an AFM here, if I control the topography, this is the image I get, okay? So this is the lower situation, this is the higher situation because you have the talc here. So I see the interface. Now, let's make a Raman spectrum here and a Raman spectrum there. This is what you have in red and blue here. And notice that when you look into these two peaks, the two Raman peaks, there are differences. There is a slight shift, and these are the two peaks that the Korean fellows established that you can use to characterize strain or doping, okay? And actually what we see here, which is very interesting, is the following. Okay, here is the connection, here is the junction, okay? And if I look now into the intensity of a given peak, and I cross the junction, I see that there is actually an oscillation, okay? Let's make a line here. Look at the intensity of this Raman feature normalized by the other feature. These are the two features established by the Koreans. This intensity ratio, it has one level when you are in talc, And then in the interface, it goes up, down, and up again, and then it goes into another level, okay? This is very interesting because what you have here is you are measuring doping, so the material is heavily doped here and lightly doped here. And the interface, you have an oscillation because every time you have, here is a PN junction, okay, which is the most common. Every time you have a junction, you have in the middle a deflection layer. And when you control this deflection layer, this is what you do when you have to control a transistor, like the 0, 1 in a computer, means having current going through or not having current going through. And the way you do it is controlling this deflection region of charges. And we could nicely see this deflection region optically. And again, look, this is only 100 nanometers, okay? And if I go now to the MOS2 and I do something similar, I also have a junction here, okay, the small doping, half doping. But now I will look into the luminescence, and I see that, again, if I look into the blue or the red area, I have different luminescence spectrum. And the MOS2 has the formation of excitons. Excitons is when you excite an electron, and the electron hole pair bind to one to another, and you form this entity that's called an exciton. And if you dope the material and you have a charge in the exciton, you have a trion, okay? And what we see is that the different doping ranges have a photoluminescence that is very different. And if I now image the difference in frequency between these two excitonic responses, this was also established in 2013 by some other fellows here. This is also a way of you measuring doping in this semiconductor MOS2. And again, if you look here, it's blue, red, blue, red. Again, you are measuring the depletion region, but you also have some sort of oscillations that you nicely see happening here, okay? And again, all these information now obtained optically in the Nano Optics regime, because you can scan the nano antenna. All right, now I introduced this conversation saying that controlling electricity and then controlling electronics was very important. And now people are talking about twistronics. Twistronics is a way of controlling the electronic properties of material with a twist. So let's talk about this twist, okay? What you see here is a graphene sheet. Every black bullet here is a carbon atom bound to each other in this hexagonal structure. Let's place another graphene sheet on top. Okay, this is a bilayer graphene, okay? And the bilayer graphene, the most stable situation, this is what you find in graphite, is when the top layer, the atom of the top layer falls, one of the atoms in the top layer falls exactly in the middle of the hexagon of the bottom layer. This is called AB stacking, okay? Now, let's twist one of the layers. This is what's happening now. I think you can see that when you twist the two structures, you have a kind of superstructure that shows up. And this superstructure depends on the angle of rotation. This is the basics of twistronics. The twistronics means you change the material by placing two material on top of two-dimensional material on top of each other and rotating one with respect to the other, okay? So here is a twisted bilayer graphene. This is the name, or this is the twisted bilayer graphene. Here is the superstructure that repeats itself because you have this periodicity in the, you have the hexagonal periodicity in this twisted system. And this enlarged unit cell in the real space generates a change in the so-called Brillouin zone or reciprocal space. The real space is where the atoms are. The reciprocal space is where the waves, like vibrational modes or electronic waves, where they live. Let's say like this. Here you say where are the atoms. Here you say what are the wavelength of the different excitonic, electronic, phononic properties. And the fact is, generating this large periodicity also generates different periodicity in the wave space or in the reciprocal space. And it's very interesting that when you do this, you start to see, for example, here again, this is the Raman spectrum. This is scattering frequency. This is scattering intensity. This peak here comes from silicon because the twisted bilayer graphene was deposited on silicon. So you see silicon here. This peak here is the carbon-carbon stretching from the bilayer system. And then you have these tiny peaks that all over with stars. And these tiny peaks, if you see, the frequency changes when you change the rotation between the two layers, okay? And what happens is that when you change the angle here, the twist angle, you are changing the size of this vector of periodicity, and you are spanning the so-called Brillouin zone of the material, and these are the phonon structures. So what you see here is the entire phonon structure, the entire vibrational mode structure of the material by just twisting one layer with respect to the other, okay? Now let's look into the electronic structure. These are the electronic band structures. These are the electron bands. And when you have a situation like this, that is the band gets flat here with respect to this momentum axis, you have a strong, let's say, density of electronic states at this given energy, okay? And what we see is that if you rotate the angle, the electronics, here is the angle is 9.4, 13.2, 21.8. The distance in energy between these two levels increase. What this means is that if you look into the optical spectrum, like at which energy the material absorbs light, the peak in the optical spectrum will be, the energy of this peak will depend also on the angle of rotation, okay? And one very important thing happens when you have a rotation angle that is exactly 1.1 degrees. And then what the electronic structure generates a flat band right in the Fermi level, right in the energy where you have where you divide the band, the conduction band and the valence band. And this generates a high density of states here, which is demonstrated here, okay? This is, you have a lot of states at this energy, and this was observed that at this situation, graphene becomes a superconductor. Okay. So notice that just by rotating one layer with respect to the other, you are completely changing the all the electronic, phononic, and all the properties of these materials. And one last piece of information about this topic. Here I represent with red and gray bullets. I represent the top and bottom layers, okay? Where I name AA here is when the top layer falls exactly on top of the bottom layer. So one atom falls on top of the other. Here where I call AB is the same situation I told you before, is you have one atom of the top exactly at the center of the hexagon from the bottom. And if I look here, let's say that the gray atom will be in the middle. If I call here, the red atom will be in the middle. So I will call it AB and BA, okay? What happens if the angle of rotation is too small is that this situation is not stable. and the material will naturally rotate back to the AB stacking, okay? The AB stacking is that one where this atom falls on the middle of the hexagon of the other. However, the direction of rotation will be different in this area and in this area, and consequently, in the middle, there will be a domain wall, and this will be a strain soliton. It will be a soliton of strain, okay? It's a region of high strain for you to move from rotation counterclockwise to rotation clockwise. And in the middle, you have this AA structure, okay? All right, let's summarize. If I rotate graphene, the hexagon between 0 and 30, you have all the possible situations. If you go over 30, it repeats back, okay? So rotating from 30 down to almost 1 degree, you have many properties that depend on the angle, like the optical absorption. At exactly 1.1 degree, you have the magic angle, strong correlation, and superconductivity. And below this angle, you have atomic reconstruction. So these are a plethora of things that happen with the twisted bilayer. All right, so I remind you of these structures, and now we want to look at this optically. And this is what you have on this picture, okay? What you see here in this brownish is an atomic force microscopy image, so it's the topography. In the topography, what you see is basically junk, okay? You see all this dust, all this stuff. This junk also shows up here. This is the optical spectra. This is the nano-optical spectra. And in the nano-optical spectra, you see the formation of these strange solitons or these domain walls between AB and BA stacked regions. So you cannot see this in topography, but you can see on the optical spectrum, okay? And you can ask yourself, okay, now that I can see, can I measure, for example, the thickness of this soliton of strain? Can I know exactly what's the thickness from moving from the AB situation to the BA? Yes, you can, but to do this, you need to understand the illumination of your system. So let's look into the illumination of the system. This is, again, a Raman spectrum. This is a large graphene particle. This is a very small graphene particle. If I zoom on this, what you see is a donut light structure. So it's funny because you say, okay, this is a particle or it's a donut. It's a particle being illuminated by a donut. What happens when you illuminate the material? This would be our nano antenna. And imagine that you have a dipole here in that antenna. So you have a strong Z field here, but in the plane, let's call the plane XY, the illumination of polarization along the plane actually will look like this. If I look this distribution from the top, I will see an illumination like this. And what happens is that graphene do not respond to light polarized perpendicular to the graphene plane. It only responds to light polarized along the plane, which is perpendicular to the antenna itself. Then the illumination has this shape, and this is what you're seeing here. The particle that was being imaged was much smaller than the illumination area itself. So what you did with with the graphene nanoparticle was you made a picture of your illumination area. Okay, now I can go back to the situation that I started on the beginning and look how the intensity, when I cross the graphene edge, how the intensity goes up and decay. And when I make the convolution of this with this donut illumination, I know that the emission from the edge actually is 0 when you are outside graphene. It's maximum when you are at the edge, and then it decays almost exponentially when you go off the graphene. And if you remember, at the beginning I said, oh, the green area of graphene is where the graphene node, the defect exists. What we are imaging here directly is that green area from the beginning. And I can do the same with the strain soliton. So here's the soliton of strain. Here is one AB and BA areas. And if I now do the deconvolution of the donut illumination, I see that the soliton of strain has 12 nanometers, okay? And when you look at STM image, this is exactly what you get. Okay, let's go further and see what all sorts of information, physics and science that you can obtain by imaging these moire structures, by imaging the structure and looking into all the information that you get from the several peaks in graphene. All right, one is, it has been established in the literature, this is a 2006 paper, where a group from Cambridge in England, they demonstrated that the line shape of a given vibrational mode tells you if you have 1 layer, 2 layers, 5 layers. And when we now do this locally with our nano, this is 100 nanometers, our nano antenna, you see that this kind of line shape, which represents 2 layers, but specifically this was made by 2 layers with AB stacking, what you see is that this line shape is exactly on the region where we were induced to say that this was AB stacked region, AB or BA. And when you look at the strain solitons, the line shape changes completely. This is what you see. This is the line shape that you get in these regions, because the electronic structure and the phonon structure at these locations, nanometer resolution, they are different. Okay. Going further, if I now look into the main peak, the main Raman peak, that's carbon-carbon stretching, if you have the AB stacked bilayer, you have a very specific frequency here. But when you have these superstructures, what you generate is a lot of modes that are activated. And what the theoreticians, again, the theory here is tight binding, but it's a tight binding with thousands of atoms and overlapping integrals and etc. to account for the supercell, to be able to measure these localized states, okay? And what these fellows predict is that the phonons at higher frequency, they are localized at the strain solitons. And the phonons at lower frequencies, they are localized at the AA points, okay? And what we do is, when you go with our nano optical system, we see that you have exactly lower frequency phonons localized at the AA sites as predicted, and we have higher frequency phonons localized at the solitons as predicted theoretically. And interesting also is to look at the width of this peak. I was telling you that the width of a peak is related to this uncertainty that you have on the frequency of this peak, okay? And what we see again is that along the soliton lines and along in these AA dots, AA points, you have this peak getting broad. So why does it get broad there? This has to do with the so-called breakdown of the adiabatic approximation. So what's the adiabatic approximation? Usually we treat the electronic structure that is represented by this cone different from the phonon structure that is represented by the atoms moving here. So in the adiabatic approximation, you say that when the atoms move, the electrons, they are much faster, so they thermalize and they do not care about the movement. And what these fellows demonstrated in 2007 was that the electrons in graphene, they do care about the movement of the atoms. It's like if you shake a glass of wine and the electronic structure will be shaking on the material. And they demonstrated that you can measure this very nicely by measuring the phonon line width, the line width of the Raman peak. Why? Because the phonon can decay into an electron hole pair, and this phonon decay is decreasing the phonon lifetime, and from the uncertainty process, it's if you decrease the phonon lifetime, you increase the uncertainty on energy. And what they demonstrated by gating the material, by doping the material, was that the phonon line width decreases when you dope the material either P or N. Why? Because when you dope the material, you take this level and put it up here. But if you fill the electronic structure up to here, you cannot generate this transition anymore. Because of the Pauli exclusion principle, you cannot take one electron and put into a level that is already full. So if you dope the material up here, this level is full. Then you kill this process and the phonon line width decreases because the phonon lifetime increases. All right, I will jump further here just to go to the Nano Optics and say, okay, what happens if you look into the line width of this peak by moving along the structure of the moire pattern in the twisted bilayer graphene? You see the line width going up and down, and the lowest level is when you cross the AB and BA stacking situation. And when you cross the strange soliton, you have a peak, or when you walk on the strange soliton, you have the same level. And when you reach these AA points, you have the highest situation. And this is related to the electronic structure of the system, because the AA location has a strong electronic density of states at this Fermi, at the so-called neutrality point, at the Fermi level of the undoped material. This generates a lot of electron phonon scattering. The phonon are killed, so the lifetime decreases, the energy increases, the energy uncertainty increases. These strange solitons, they also have peaks here, and this energy is exactly the phonon energy, so they also like to kill phonons. And then you can understand all these related to the phonon lifetime. And to finish, we measured the phonon lifetime by changing the rotation angle, the twist angle between 0 and 3, and we demonstrated that the phonon line width is maximum at the magic angle. So this is the situation where you have the best, let's say, electron-phonon coupling all over the material, and this is the relay also where you have superconductivity, although the superconductivity in graphene is not necessarily related to phonons, and this is still under study. And since I'm looking to my time, I will end my talk here with acknowledgements. Okay, and these are just the pictures of the people who had somehow worked on this project. Okay, a lot of fellows from Brazil. Andrej did, he was a postdoc, he did a lot of these nano optics measurements. But we had help also from these fellows that did scanning probe measurements and many others. And we had collaboration with Tiago from Imetro, Eliel from Bahia, Rafael from Pará. And the theory was developed by Vincent Meunier in New York and Jean-Christophe Charlier and their group in Belgium. And with this, I thank you for your attention.
Thank you very much, Ado, for the very interesting presentation. So we are open to questions now. Does anyone have a question? Bernanke.
Okay, I think Kyle has his
his hand. Yeah, Caio, go ahead, please.
Okay, so yeah, thank you very much. It was very interesting, but also very dense. It was hard to follow all the details. It's amazing work. So let me ask you something about the thing which is not so hot, but also very interesting about the homopolar junctions. So I actually, and I'm asking you this because I actually missed something very fundamental, and probably you can explain it there more easily. So if you flash the slides with the talk and yeah, so I missed the very fundamental thing, which is you have here strain and doping, right? And once you do the Raman measurement, you are more sensitive to what? To the doping because of the population of the electrons, or what? This I didn't get the feeling.
Yeah. So Caio, you're very fair question, because I didn't explain a very fundamental aspect, which is how do you know if you are looking at strain or doping or both? Mm-hmm. And you are right that both strain and doping change the frequency of these peaks, the frequency, the intensity, etc. Okay, but what was established by those Korean guys, this work here, what they showed was the following: if you have a graphene system, and you measure different locations with different doping, the frequency of the two peaks, they change with a given slope. If you plot the frequency of one with respect to the frequency of the other. However, if what is changing the frequency is strain and not doping, the slope of the plot of one frequency versus the other is different. So what he demonstrated is that by looking at the slope of the change in frequency, you know if this is strain or doping, or both, if things go into the middle. And what we were able to demonstrate here, and this is what I didn't go into detail, is that what is generating the change here is doping and not the strain. Okay.
Okay, wonderful. Then related to that, a quick question. So if you go one slide further, or one or two, you see some nice oscillations. I guess the next one.
Yeah.
Yeah. So I mean, normally if you have a homopolar junction, whatever junction, you get this plateau in this nice transition region. Do you understand why you have so strong oscillation, and when you have this the silicon disulfide dioxide?
You know, to be honest, the answer is yes. And just tell you how experimental life is, right? When I saw this, I found it beautiful, and I wanted to have very fancy explanation related to the electronic structure, maybe plasmonics or something like this. But actually, these very same oscillation can be seen in the topography measurement with AFM. So this is just the following. When we laid the MOS2, when we laid it down here, this is the bottom region. Okay, it falls there with wrinkles.
I see.
Mm-hmm. You know, and so these are, let's say, this is a bad device.
I see. So there is this relation between the wrinkles and the doping, and yeah, okay.
Exactly. Yeah.
All right.
And this is all about touching or not touching the substrate, you know. So,
yeah. Okay. Good. So I let the other guys have opportunity to ask. So so many things to discuss. Yeah. Great. Thank you very much.
Thank you.
Yeah. Wernicke, do you have a question? There is no one else with raised hand, it seems.
Yeah, go ahead, George. You can make your question. I have my opportunity.
Yeah. I was curious about these localized phonons. Could you talk a little bit more about that? What exactly do you mean by localized phonons? They because we think of phonons as a vibration that is going through the material. So what exactly is that?
Yes. So very good question also. So the point is, when we think of you already start the answer. When we think about phonons, electrons, you think about something that is in the entire material, right? You define a periodicity of the unit cell, and then you replicate this thing, and what happens inside one unit cell will happen all over the material, and well, of course, with a given periodicity, etc. But what we see here is that if you go, and again, this is 100 nanometers, so this entire range here is like 300 by 300 nanometer, okay? So the phonons that you see here, they are different in frequency from the phonons that you see here.
Okay.
So that specific frequency is localized at this region. The same happens, but you know, this peak here is only observed at this location. So it's you have a material that you cannot represent this material with something that is all over. That thing is localized at this point.
Okay.
And yeah, and then to represent this theoretically, you must make a model with a huge unit cell of thousands of atoms and overlap integrals and etc., for you to be able to represent something that's localized at that location.
So it's localized especially, and it's not moving.
Exactly.
Okay. Okay.
The same, let me remind you about this, the same for this density of states, okay? So this is the local density of electronic states. So this peak of electrons here only happen at this point. If you move here, you don't have these electrons there anymore. And again, this is theoretical. Is again, you have a huge unit cell, and then you can localize the electronic state at that position.
Okay. Okay. Very interesting.
And they're stuck there because of the structure that let me find. Yep. They're stuck here, okay? These high density of states they're stuck at this location because the material is different here, the material is different there.
Okay. Okay.
And the phonons, they are localized around the regions where you have a strong gradient of strain, or there is no relation to that.
Look, there are two. Let me put this way. They are all localized, but there are three very different situations here. One situation is the usual A-B stacking. The other situation is the soliton of strain here, that there is a strain that modulates from here down there. And you are right that there is a quite strong interaction in these AA regions, because this is where one atom wants to be exactly on top of each other. And this is very unlikely, this is very unstable, this is very bad for the atoms. And this is where the strong localization happens, and this is where the flat bands appear.
Yeah, because you see, just a naive way of thinking this is if you have a homogeneous solid, then whatever George was saying is that with standard condensed matter physics, we have this beautiful delocalized phonons. But once you have strain in different domains, the phonons, they reflect this non-homogeneity, and they are constrained somewhat to vibrate. I mean, the vibration are constrained to this inhomogeneities, I guess. This is why I ask you.
Yeah, that's okay. Exactly correct. Yeah.
Sorry.
Yeah, sure, sure. You made a comment about finding strong electron-phonon interaction exactly in the places where people have seen superconductivity.
Yeah.
I assume that the people who are claiming that this is unconventional superconductivity were not very happy, right?
That is so. There are papers in the literature saying that electron phonon is very strong in this range, so the phonons might play a role. But at the same time, you are right. There is people saying that the superconductivity in this material has nothing to do with phonons.
Mm-hmm.
And this information that I add here only confirm that you have strong electron phonon coupling, but this doesn't mean superconductivity is due to it.
Okay.
So, yeah.
Luis has a question. Luis Nunes.
Yes, thank you, George. Very nice, Ado. Wonderful.
Thank you, Luis.
All right. I have a question about this business of the breakdown of Born-Oppenheimer approximation. Right?
Okay.
You mentioned that you have 2 time scales, and I could understand that. What I couldn't understand is how that is related to this phonon structures. Can you explain that again?
Okay, so I will rephrase it, okay? So what was established back in 2007 is that if you want to treat phonons properly in graphene, you must include electron-phonon interaction.
Yep.
You cannot adopt the diabatic approximation and go along with the phonons without care, okay?
Right.
And then the way people they found to prove this. So all these papers that I cite here are related to this. Okay, it's cone anomalies in electron-phonon interaction, graphite, etc. The way they proved was to show that when you gate dope the graphite, you change the phonon line width. So they fully demonstrated that you cannot neglect the electronic structure when looking into phonons.
Yes. Okay.
And the way we understood, the way they explained, and we now understand, is that the reason why the electrons change, well, the way you can model the electron-phonon interaction is by assuming that because graphene, this is the electronic structure, okay? It's the cone structure of graphene. So usually when it's not doped, this level here, let's call it this the Fermi level, should be here, okay? And then because this is a zero gap semiconductor, the phonon can generate an electron hole pair.
Right.
So the phonon decays into an electron hole pair. So the fact that you can have this process decreases the phonon line lifetime,
right,
and consequently increases the phonon line width.
Mm-hmm.
And once you dope the material, which means you move the Fermi level up to somewhere here, then the process cannot happen anymore because you fill it up. And then the phonon line width decreases because the process of phonon decay cannot happen anymore.
Okay, right.
So, yeah, this is what was fully explained. And one thing that I jumped, but it was very interesting, was that very old material, like in the 70s, people were studying the so-called graphite intercalated compounds. And graphite intercalated compounds is when you dope graphite with metals or whatever, okay? So there is a high doping, and this is on the basis of our ion lithium battery, okay? These are the electrodes of ion lithium battery. And what they showed on the Raman spectrum is that if you look at the peak of graphite and you go to intercalated compound, the peak gets very broad and asymmetric. And this is again because of this electron-phonon interaction that back then people didn't really explain. And the same happens for carbon nanotubes. Carbon nanotubes, they can be semiconductors or metallic. And when they are metallic, the G band gets very broad. Again, this is all about the same process of the cone anomaly or the breakdown of the adiabatic approximation.
Yeah. Okay, so then according to this picture, depending on the amount of doping you have, there will be two classes of phonons, ones that can decay because they have large energy, and the ones that cannot decay because they don't have enough energy, right? So this can be observed.
Okay, you are absolutely right. But then one specificity, let me see, I can show you utilizing, just a second. Okay, this is the phonon diagram of graphene, okay?
Okay.
And the only Raman active phonon in graphene is this guy here. And it's the highest frequency one. So what you proposed, which is very interesting, I would have very, very hard time to see just because I don't have many peaks to look at. You see, I only have this guy. Then I can only see when the doping kills the process for this guy or does not kill the process for this guy. It would be very nice looking at many others, and maybe this is possible with the twisted bilayer, because I showed you that with the twisted bilayer you can see many peaks.
Yeah, that's what I had in mind. So
yeah,
looked at this question.
That's a very interesting proposal. I can try to do this experimentally.
Okay, thank you very much.
Thank you.
Thank you, Ado, for very nice talk. Thank you, Luis. I have a comment precisely in that last part of this question. In that, if you are able to see probably this phonon, this different family of phonon will be localized in different position of your material. Is that right? Because they will be localized at different positions because they have different energies, so strain will localize different phonon in different position of your lattice.
Yes, that's right. It's like what you see here. It's these like 4 structure phonons here. They are localized at the AB stacked regions. This more like single peak structure is localized in a different location. So you're right. It's every place you look, you see the localization of one specific vibrational structure.
Very nice. Very nice.
Yeah.
Thank you.
Well, thank you.
I'm curious how much, not that we are planning to buy, but how much does it cost one of these devices that you guys are building?
You mean the equipment to make the nano optics?
Yeah.
You know what defines the price is the market for this kind of instrument, and this kind of instrument. And when I say this kind of instrument is the usual micro-Raman spectrometer. They are in the range of 300 to 600,000 euros.
Okay.
So the guys, they have in mind selling this system by something like 400,000 euros.
Okay.
This is the price of such a system.
So, so you said they are planning to sell, so the equipment is not ready to be marketed yet.
No, it's this is their price, and they sold the first equipment already to Germany. Okay. And they had a selling kind of on hold to Penn State in United States because they want some sort of customer service that these guys are not able to do in the United States. You know, they can do it here. if you buy one in Uberlândia, they can go to Uberlândia very quickly.
Sure.
But this one is on hold. But when I say they are planning, is because they have some freedom to discuss, and the system can be naked or very well dressed by many options, and so this is.
So there is a range of types.
Yeah.
Very customizable.
Exactly.
That's very, very uplifting to know that we are being able to sell instruments like that to Germany. It used to be the opposite, right?
Yeah. You're right. Yeah, we are very happy about this.
Yeah. I am sure.
Yeah.
So I don't see any other raised hands. So if there are no more questions, we should thank the speaker again for this very nice talk. Thank you very much.
Thank you. Thanks for the invitation. It was great.
Thank you.
And I